Hi everyone, my name is Francesco De Fazio and I'm a product designer from Philips Experience Design, specialized in design for the circular economy. Together with my co-authors from Delft University of Technology, we created a new design methodology that we call the Disassembly Map. This is a method meant to guide product design for disassembly. But first of all, why is design for disassembly becoming more and more relevant? In the recent years, we saw how consumers are becoming more sensitive to the topic of sustainability and that they are demanding changes from legislators and producers. The European Commission has quickly started to respond to these requests by committing to accelerate the transition towards a circular economy through the European Green Deal and a new circular economy action plan. At the same time, producers like Philips offer multiple service activities, like refurbishment of big medical equipment and repair and reprocessing of certain consumer products. Furthermore, circular business models like subscriptions-based models and sales of refurbished products are becoming more and more common. Design for disassembly is fundamental to future-proof new designs by anticipating possible future regulations, improving quality and efficiency of the current service activities, and enabling new circular business models by helping to making them economically feasible. The disassembly map is a modeling method meant for product designers and mechanical engineers, and it is based on the latest standards and research from the European Commission concerning the assessment of the ability to repair, reuse, and upgrade energy-related products. It can be used in early stages of the design process, when design changes are still possible, by assessing either initial CAD model, prototypes, previous design generations, or competitor products. These by visually representing the architecture of a product, describing the disassembly precedence and dependency of components, and the operations necessary for their complete non-destructive removal. The creation of these methods started in 2019. During a first study, we assessed the ability to repair and upgrade 7 consumer products. In this instance, we focus on a single product group, vacuum cleaners, from different product categories, brands, and price ranges. The outcome of this first study have been documented in a paper submitted to the Journal of Cleaner Production. However, we are constantly working with this design method, and since that first study, we have iterated on its original version. The outcomes of the second iterations are contained in the article submitted for this conference. Since the paper related to the first study has not been published yet, we will dedicate a part of this presentation to revisit some of the main aspects of the initial iteration. This will help to better understand the improvements developed in this second study. In the first study, the 7 products were assessed based on the preliminary version of the European standard EN4554 and the scoring system for repair and upgrade of products, developed by the European Commission Joint Research Center in 2019. They both indicated 4 main product-related parameters for the assessment of design for disassembly. These are disassembly depth, fasteners reusability and reversibility, type of disassembly tools, and disassembly time. Disassembly depth is the number of steps required to remove a part from a product in a non-destructive way. According to the EN 45554, a step can be defined as an operation that finishes with the removal of a part and or with a change of tool. As indicated by the standard, the entire assessment was focused on the disassembly of priority parts. What determines a priority part is the likelihood of the need to replace or upgrade the part, the suitability of the part for use, and the functionality of the part. Fasteners reusability and reversibility is considered closely interlinked with the type of tools and the level of skills required to complete the disassembly. For these parameters, 3 classes of assessment were used. Tools were instead assessed based on 5 classes. In this case, the EN45554 provides a list of tools considered commonly available. Finally, also disassembly time was taken into account. Time can be used as an indicator of the level of difficulty of each disassembly action, part of a step. As shown by the examples on the right, the same amount of steps can actually determine very different disassembly times due to the different actions involved. Time was assessed using the EDIM, Ease of Disassembly metric. This is a metric developed in 2016 by the European Research Centre. The EDIM is based on the MOST, Minor Operation Sequence Technique. This is a predetermined motion time system based on sequence models, composed by a set of sub-activities. Sequence models, as shown in the bottom left of the slides, are multi-character representation of a single activity. Each sequence model is composed by sub-activities, individual basic motions, represented by parameters. On the bottom left, you can see the parameters representing sub-activities like gaining control, placing, fastening, and loosening. Indexes are indicated next to the parameters to express variation in action time based on task condition. On the left, you can see an example of indexing proposed by the Joint Research Center, where an increasement of the force necessary to release a connector increases the index of the loosening parameter L. On the right, you can instead see how the total amount of indexes included in a sequence model can be easily translated in the amount of seconds necessary to carry out the related disassembly operation. Here you can see the MOST sequence used to describe the unfastening and removal of a screw from its sole. The sequence describes the sequential actions necessary to get a screwdriver within reach, to position the tool on the fastener, to turn the wrist for 9 times to unfasten the screw, to reach and grab the screw, and finally to remove it from its sole. This method was used to code and calculate the disassembly time required for more than 200 disassembly operations. An EDIM metric was created for each product, and disassembly time was calculated for the disassembly of each priority part. The assessment system allowed for comparison of the disassembly depth and time required to reach the same priority parts in different products, and eventually for calculation of a final aggregated score on a scale from 1 to 10. Although this assessment allows to compare and score different products based on design for disassembly, it does not provide clear redesign insights. At the end of this evaluation, it was not clear how to translate this numerical assessment in practical redesign solution. The key to solve this translation problem came out of a literature research on studies about design for assembly, disassembly, and end of life. In many of the sources analyzed, different types of diagrams were used to support the identification of redesigned solutions. In these slides, we listed the main ones that inspired the work we will show now. So what we identified as a possible solutions to translate a numerical assessment in something easier to interpret and meant to support redesign activities is a single representation of the 4 parameters for the assessment of design for disassembly. Something simple to interpret, replicable, based on standard rules, but still flexible enough to represent very different architectures and product configurations. Based on the literature briefly shown before, we identified 3 main logic representations, which allow to represent different types of disassembly dependencies in a standardized and comparable way. Components are indicated in circles. Sequence-dependent disassembly is indicated with a sequence of circles, positions one after the other on the vertical axis. Sequence-independent components are instead represented one next to the other on the horizontal axis. The symbol AND is used to represent multiple dependency. This is the disassembly of a component dependent by the disassembly of two or more components, independently disassemblable from each other. We also integrated the representation of component clustering and alternative disassembly sequences. These two logic representations are necessary since, in accordance with the Joint Research Center scoring system, the assessment of disassembly should focus mainly on the fastest and easiest disassembly sequence to remove priority parts. By using these standard logic representations, the overall visualization of disassembly depth becomes intuitive. The vertical dimension of the diagram expresses the sequential disassembly depth of the product. On the other hand, the horizontal dimension indicates sequence independency of disassembly operation. The representation of disassembly time has been integrated by using action blocks. These are visual elements that indicate disassembly actions happening between steps. They are positioned in between component circles. The appearance of the action blocks is coded to represent the impact of different product design related features on disassembly time. In the table on the right, you can see the most sequences used to describe some of the most common operations encountered in the assessment of vacuum cleaners. Different colors and shapes are used to indicate variation in action time. Our aim is to indicate product design related features causing this variation, highlighting those operations that require the highest time. Finally, different color tones are used to express variation in parameter indexing, for instance, caused by different level of force intensity. By combining the representation of disassembly depth and time, we obtain a single complete visualization, which not only provides information about sequence dependency and independency, but it also highlights the operations between steps, which requires the highest time. 4 main penalties were defined based on the EN 4554 and the EDIM, and represented using icons. The most relevant components for circular design strategies are highlighted in the map using target indicators. In this case, we decided not only to indicate the priority components defined based on failure frequencies, relevant for design for repair, but also those components with the highest embedded environmental impact and economic value. These are relevant for other circular related design strategies, like design for part harvesting and recycling. The resulting disassembly map is easy to read and interpret. As already said, the vertical and horizontal dimensions indicate the overall disassembly depth of the product, and the operations sequentially dependent and independent from each other. The action blocks show the type of operations taking place between each step, and their impact on disassembly time. Penalty icons help to spot operations requiring uncommon tools, hidden and or non-reusable connect fasteners, and product manipulation. Finally, target indicators highlight where target components are located in the overall product architecture. Two main strategies to enhance the design of a product for disassembly are limiting sequential disassembly operation, shortening the length of the map in the vertical dimension, and moving all the target components as close as possible to the disassembly surface of the product. To prove the efficacy of this method, a vacuum cleaner was redesigned in the first study. Here you can see how most of the target components were positioned beneath multiple layers of plastic cosmetic parts. In the original design, multiple sequential disassembly steps must be carried out to completely remove them. The operations involved include many hidden snippets requiring high unfastening force. Additionally, an alternation of different types of tools is necessary. These features determine a high disassembly time to remove parts with low priority, but that had to be disassembled to reach the internal components. What was proposed as a possible redesign solution is to clamp all these low priority parts in one single cluster that can be disassembled in one step instead of 6. This by simply repositioning 3 screws which connected the internal motor housing to the upper cosmetic parts, in such a way that these key screws could be reached from the outside of the product. The guided redesign turned out to be extremely effective by decreasing of almost 50% the disassembly time of the main priority parts. However, this first study had a main limitation. The method was created and tested by analyzing one single product group. So the second study we are presenting today had the aim to determine the versatility of the disassembly map for other type of consumer products, and if necessary, to improve the method. 4 products were selected from different product groups, brands, and price ranges: a coffee maker, a pressurized steam generator, a washing machine, and a child car seat. The products were fully disassembled, following the fastest and most effective sequences, and all procedures were video recorded for later reference. The original disassembly map method was used for the assessment, and if limitations were encountered, the basic mode was used to define the new sequences. Identified improvements were further developed and formalized in new guidelines for the method. And lastly, the disassembly maps obtained were drawn digitally. 3 main improvements were identified: a more extensive representation of disassembly actions, a more precise representation of the final removal of a component, and a more consistent visual representation of disassembly depth. The original action blocks coding system was based on the assessment of vacuum cleaners, thus optimized for the representation of those operations found in that specific product group. These were mainly snap fits, friction fits, and screws, mostly of the same type and length. In the products analyzed in this second study, a much wider range of connectors and tools was encountered, which required the creation of a more extensive coding system. To do so, all the disassembly actions analyzed in these second studies have been grouped in 2 main categories. The first category is single motion actions. These require one single loosening movement, and variation in disassembly time are mainly determined by the level of force applied. These type of actions have been represented using rectangular action blocks. An example of single motion actions is a snap fit released by applying force using a spudger. The second category is multiple motion actions. These require multiple loosening movements, and variation in disassembly time are mainly determined by the number of motion repetition. Compared to single motion action, in this case an additional action of removal of the unfastening connector is required. An example of multiple motion actions is the unfastening of a screw, which requires multiple repetitive wrist turns. Similar to the original coding, the base color of the action blocks expresses if the disassembly operation is carried out simply by hand or if it requires the use of a tool. This differentiation is important since having to fetch, change, and put back a tool determines additional disassembly time. As in the original coding, different color tones are used to visualize 3 levels of motion intensity, thus variation in operation time. The new extensive coding system has been translated in these 2 tables. These tables guide the correct coding of a wide range of operations, ensuring assessment comparability. Actions have been coded based on the indexing indicated by the most for the parameter L, representing loosening action. The lower you look in the table, the higher the disassembly time. A second improvement identified in this study is a more precise representation of the final removal of a component. In accordance with the Eading method, in the first study, the action of final removal of a component was considered a standard task, with a standard time of 1.4 seconds. However, in this second study, many different types of final removal actions were encountered, with a significant variation in disassembly time. In fact, you can easily imagine how the time required to remove a lightweight component, like a coffee maker clip, is quite different compared to removing a heavy concrete counterweight of a washing machine. For this reason, different types of removal actions were coded based on the basic most, as you can see on the right. Finally, in this second study, a standard grid was used to ensure a more consistent representation of disassembly depth, improving comparability of different maps. This grid maintains a constant spacing between each component circle, action blocks, and possible logic connections. Here you can see the resulting 4 disassembly map, expressing clear differences in architecture morphology. The standard grid helps to compare the position of specific components and actions in the overall architecture, and it allows to intuitively compare the overall disassembly depth of the 4 different products. Based on the new coding system, it can be intuitively observed how in the disassembly map of the washing machine, on the left, there are many multiple motion actions, represented using hexagonal action blocks. On the contrary, in the disassembly map of the coffee maker, on the right, we can observe mostly rectangular action blocks, representing single motion disassembly actions. Based on the logic representations used to visualize disassembly depth, it can be easily observed how the map of the child car seat, on the left, develops mainly in the vertical dimension, indicating prevalence of sequence-dependent disassembly operation. On the contrary, in the disassembly map of the pressurized steam generator, we can observe how many components can be disassembled independently from each other. In this case, the disassembly operations are represented mostly on the horizontal dimension. These are some examples of features that contribute to the ease of disassembly of a product and how they will be represented in the map. Target components should be as close as possible to the top of the map, indicating that they are easily accessible in a minimum amount of steps. The overall orientation of the map should be as horizontal as possible, indicating that many components can be disassembled independently from each other. As many action blocks as possible should be rectangular and green, indicating that many disassembly operations can be carried out with a single motion action and without the need of a tool. The color and shape of action blocks should be as constant as possible throughout the map, indicating that the same type of tools are used and that they don't have to be interchanged often. Finally, no penalty icons should be present in the map, indicating that all fasteners are reusable, connectors are visible and easy to reach, the product does not need to be manipulated to reach fasteners, and only common tools are necessary. The main conclusions of our study are that the representation of disassembly depth identified in the previous study allowed the complete mapping of the 4 new products categories analyzed in this study. The new action block coding system defined in this study allowed for representing a larger diversity of operation. Furthermore, clearer guidelines for the correct coding and representation of action blocks ensure better results comparability. The additional coding of the action of final removal of a component allowed to take into account different disassembly conditions, like part weight, which determines variation in disassembly time. Finally, the use of a standard grid allowed a more uniform representation of disassembly depth, thus facilitating comparison between maps. However, the method still presents some limitation. Some actions, like desoldering, have not been studied yet. Even this more extensive coding system might not be able to cover all the disassembly operations that could be encountered in consumer products. Additionally, the vertical grid cannot yet be considered a reliable indicator of disassembly depth, since it is influenced not only by the number of disassembly steps, but also by the number of action blocks. And to conclude, it is recommended to investigate a wider range of products to test the versatility of the method even further. Thank you all for your attention. We would love to see how this method may support your work. Please feel free to share your experience and feedback for improvements. Both at Philips and TU Delft, we are constantly exploring new design tools and methods to guide product design for the circular economy. So don't hesitate to contact us with ideas that we could explore together.